So let's now consider a concrete example. So this will be actually my first example. So this is an example of the quantum principle of superposition. This will be example number 1, and it's going to be some concrete case that I want to consider that's going to teach us an interesting lesson. So let's consider a concrete case to make this a little less abstract. And then my concrete case are going to be photons trapped between two mirrors, right? Two mirrors. Now for that, we're going to have, two mirrors, and mirrors, you know, are made out of conductors. So I'm going to have two perfect conductors here, conductors at either end. I'll have some kind of an x-axis, right? And I know the electric field has to be 0, of course, inside my conductors, equals 0 here. And I might plot on this axis the electric field associated with the light wave that's associated with these photons. And that electric field, you know what that's going to look like. It has to obey certain boundary conditions. It has to be 0 on the edges, and it's going to be some kind of light wave, like so. And my light wave will have a particular wavelength, say lambda. And then we know how to write down the electric field for something like this, E of x, right? It will look as follows. Because I have this, I know it's some kind of sines and cosines in here, because actually the electric field has to be 0 at x equals 0. We'll call this point x equals 0, and we'll say we'll make our distance here L. We know then that it should be some amplitude, right, times a sine, right? And then we have our wave in here. And it's the usual thing for getting the right phase in my wave. There's 2 pi radians per cycle. And the amount of cycles are measured by taking my position and dividing by my given wavelength. And that will tell me the electric field when I've got these photons trapped in here with light of a given wavelength lambda. Now, of course, I hope you guys recognize that I've got 2 pi over lambda. That is more naturally written as our wave vector k. So I have a times sine of kx. And now I have a physical question for you guys. Let's suppose I were to actually plot the momentum distribution along the x direction of these photons. Here's px. What is it that we would expect to see? Well, right, I've got a light of a given wavelength lambda, right? So I know from de Broglie I should measure a momentum p, right, which equals h over lambda, or equivalently, as we've been learning, that's just h bar times k. So there's that particular value. And I would expect that, well, my photons are going to be concentrated around one particular value, like so. And that would be correct, except that's clearly only half of the story, right? We don't just have photons with positive momentum in here. After all, these photons are bouncing back and forth between these two mirrors to set up this standing wave, right? When I do measurements of the momentum of my photons, I expect to get also the negative value here. I expect not only plus h bar k, but minus h bar k. And since they're bouncing back and forth, I expect that on average, half the time I'll find them moving to the right, and half the time I'll find them moving to the left. So in fact, I should have a distribution look something like this. My point I'm trying to convey is these two peaks have equal height. They have equal probability associated with them. So I actually have contained within this system 2 different pure states of momentum that can come out from measurements. And the question then is, well, how are they contained in my basic description of the system? And if you think about it, you begin to realize, oh, the sine function actually contains 2 terms within it. The sine function can be written as 1 over 2i times the difference in e to the I kx and e to the minus I kx. So we learn 2 lessons from this. It seems to be that these complex exponentials, one with a positive k and one with a negative k, are associated with the pure states of momentum. Pure state of p, in this case, equals plus h bar k, and this one must then be P equals minus h bar k. And we also see that we have some weights associated with these two peaks. For this peak here, the probability, right, that we are expecting for this positive peak somehow must be related to A over 2I, right? I'm not sure what this relationship is yet, but that is the weight that goes with that state in this superposition. And likewise for this peak, I have the probability is something like A over minus 2I. And the question then is, well, how do we take these weights and actually get probabilities out of them? Well, first, probabilities have to be positive. So I've got a problem. I've got a plus term and a minus term. But even worse, probabilities, of course, have to be real. And what I have here are complex numbers. So one very reasonable starting point would be to say, okay, I think it must be related then to the magnitude of the weights in the superposition, right? Now that's a very good and reasonable guess. We might be able to do it one better, but that at least is where we would start. It's got to be related to that magnitude somehow. The way we can maybe try to resolve that is go back to what we've been seeing here all along. Notice it seems whenever I calculate a probability, what I'm looking at is the magnitude of some complex number, but it's not just the magnitude. It always seems to be coming out as the magnitude squared. So I'm going to guess the probabilities are proportional somehow to these complex magnitude squareds, but I'm going to put a question mark over that because that really is a total guess. We don't know exactly how it should go, but that would seem to be one, of course, very, very reasonable guess. So the two lessons that we learned out of this example are the following. The first is that it seems that and this really is a mathematical way of phrasing another piece of de Broglie's hypothesis. When de Broglie says those waves that we superpose have wavelength lambda equals h over p, what he's really saying is that this corresponds to really that we've learned that e to the I kx is a pure state of momentum, right, with momentum p, of course, equals h bar k, which is the other way of writing the de Broglie hypothesis. But now we actually, through this example, have a particular mathematical function associated with those states. The second lesson is that it seems, although we can't say for sure, that the probability in the general quantum superposition, right, of observing a value on of an observable it seems to be proportional somehow to the weight associated with that observable, right? Its magnitude of that weight, and we are guessing here that it probably goes like the magnitude squared. Okay, very good. So that then completes what we learned from our first example of the quantum principle of superposition.